Alrighty, we are in the last video for dynamics, and we're just going to do a review of the unit to talk about the topics, concepts, and material we've covered, along with some equations, reminders for the equation sheet, and then a little bit talking about problem solving. And I think for most of you, I also went over the review document in class, so I'm not going to spend a ton of time on things with that. You can find this document in the Unit 2 folder on Schoology. Go to your resource for dynamics, that purple folder in there, and it's at the very bottom, AP1 review for dynamics. All right, so we'll start here just to walk through where we've been in Unit 1, or 2 rather. So in Unit 2, we started with an essential question. What causes the motion of objects to change? We're building off of Unit 1 and the kinematics values such as acceleration, velocity, acceleration being the main one that carries over with changing motion, right? Change in velocity is acceleration. And what causes the motion of objects to change, what causes acceleration is force. All right, so overarching ideas, we saw lots of systems of objects, whether that was Atwood's machines or other systems, even something like center of mass, which I think I forgot to put in the key concepts, but we did do center of mass. And that was similar to systems of objects. You have multiple things and you're finding the center of mass of like multiple masses. Types of forces, we have 7 types of forces that you should be familiar with. Applying Newton's laws of motion was something we did a lot, specifically the second law, or often using it with equilibrium, but just using the sum of forces was a big thing. And circular versus linear motion comes up at the end when we look at things going in circular motion. All right, we're always solving problems, so problem solving steps are, of course, relevant. Concepts and topics we've covered. Definition of a force, so you should know that any force is a push or a pull. Something like velocity is not a force, acceleration is not a force, right? Force is not how fast something is going. It's not whether it's speeding up or slowing down, acceleration. Force is the push or pull that is acting on an object. Types of forces, we have 7: gravity, friction, drag, applied, normal, tension, and friction. And you should know those 7 and be familiar enough with them that you can recognize, hey, in this problem I have some tension, and here's a force of gravity, and this is a normal force. How to solve for specific types of forces. We have equations for gravity, friction, and spring force. We'll mention those on the equation sheet. The one that isn't on the equation sheet is gravity. That one, the force of gravity equation, they expect you to be really comfortable with, because if they give you the mass of an object, they expect you to immediately be able to find the force of gravity acting on it. And if they give you that force of gravity, they expect you to be able to find the mass of the object, which luckily is not too hard using the force of gravity equation. All right, Newton's 3 laws of motion. First law, just noting that anytime an object is at rest or anytime it's at constant velocity, that means the forces are balanced on it. So we get balanced forces, meaning equilibrium. If there's an unbalanced force, if more force acts one way than the other, you get acceleration. Second law is mostly for equation purposes, which we mentioned below, but solving for things with a sum of forces equal to mass times acceleration. Third law, pairs. Keep your eyes out for problems where there are 2 objects putting forces on each other. So object 1 pushes or pulls on object 2. Object 2 then pushes or pulls back on object 1 with the same amount of force, just in the opposite direction. Equilibrium definition, so just knowing that if forces are balanced, then you have no net force, you have no acceleration. Your object is then at rest or in constant velocity motion. Using the second law can still be useful for problem solving, even if your forces add up to 0. Those forces that go into the sum of forces could still be found or worked with, or a lot of times there's useful information to be gathered from the fact that the forces are all balanced. It can help you find things, find other forces. Systems of objects, so whether it's like 3 objects or 2 objects being pushed or pulled together across a surface, or Atwood's machines are their own thing, but being aware of either contact forces between like blocks that are pushed up against each other and pushed along, so the blocks themselves are pushing on each other. Atwood's machines is, of course, the pulleys, where there's a pulley and a string over it, or multiple strings connecting 2 or 3 masses. Um, and for those, of course, tension is acting in those strings. The main thing with those systems is being aware of combined masses versus individual masses, and we'll talk about that in our reminders in a little bit. Defining direction, making sure we do clockwise, counterclockwise for those problems. Ramps, on ramp problems, making sure to think of it as we want the surface of the ramp to be the x direction. We want the into the ramp or out of the surface of the ramp perpendicular to the surface to be the y direction. And that means that we end up breaking gravity itself into some components. So that means gravity Fgx and Fgy are the parts of gravity acting either down the ramp or pulling something directly into the surface of the ramp. Circular motion, the vector variables, main ones here are tangential velocity, centripetal force, and centripetal acceleration. Omega does come up here as well. The angular velocity will show up a few times. So you have tangential velocity and centripetal acceleration or force. Tangential velocity is the velocity that is tangent to the circle. It's at a right angle to the radius of the circle. And it shows if we were to release an object from its circular motion and allow it to just keep going in the direction it's going, it would have that tangential velocity. It would fly off in that direction. Centripetal acceleration and force always end up acting inwards. If you sum up all the forces, now there could be multiple. A lot of times there's just one force acting in, but it's possible. Like in vertical circles, you can have tension and gravity both, or normal force and gravity. So you just want to sum all the forces that are acting in the in or out direction, giving you your centripetal force. And it can consist of different forces, right? Gravity could provide that centripetal force for an orbit. Gravity could affect centripetal force for vertical circles. Tension, if something's on a string or rope. Normal force, like a roller coaster loop type of situation, or even a car going down like a hill or a dip. Um, Force of static friction for something like on a rotating disc. Like we had some problems with coins or objects placed on a rotating disc. That's friction, static friction acting inwards. So yeah, those are the forces that could provide the centripetal force in different scenarios. Universal gravitation, I want to be familiar with that equation to find the force of gravity between any two objects in the universe, not just the force of gravity on Earth or on the surface of the Earth. So that's your big G m1 m2 over r squared. And then the last piece we brought in was just connecting gravitation with circular motion for orbits. So for a circular orbit, the force that's pulling on like the moon orbiting the planet or something like that, that force on the moon would be gravity. So we'd use universal gravitation for that. And then that force would be the centripetal force equal to mass times centripetal acceleration. So we would combine the gravitation equation with our circular motion equations. All right. Other things here. Now, I didn't update this. I think we'll go to the equation sheet and we'll look at it. We'll mention some things with friction. FC equals mass times AC. That's the big one. This one actually is on the sheet now. They put velocity equal to omega times r, so that's nice. They added that. Um, Other things to remember for equations or values: equilibrium, anytime that objects are at rest or moving at constant velocity. It could mean either your y forces are balanced if you have vertical equilibrium, your x forces are balanced and add up to zero if you have horizontal equilibrium. And then knowing direction of, we would sum forces in the clockwise, counterclockwise direction for Atwood's machines and pulleys. Use a sum of forces in the in-out direction for circular motion with centripetal force. Keep in mind your general problem solving steps. Just, what's provided to me, what's the situation, what's the scenario, how do I understand what's going on in the problem and what they're telling me about it. What am I asked to do or find? What tools or equations do I need to solve it? So what am I working with as far as knowledge or math skills or particular equations we use for the solution? Show your work, check your answers. We'll also run through this. I'm going to go through quickly because we're going to do a bit of a whiteboard on this too. Angled forces should be split into components. Make sure you use your trig to do that before you do sum of forces with Newton's second law. Anytime you have two-dimensional forces, stuff going on in the x and the y direction, subscripts are really helpful, especially when you split things up. with components just to remember what your X and your Y values are. Coordinate systems like ramps, when you want to have the X direction be along the surface of the ramp and whatnot. Make sure that you choose the right coordinate systems, or counterclockwise, clockwise with Atwood's machines. Equilibrium means the sum of forces is zero and you have no acceleration. In orbit problems, centripetal force is just that force of gravity with universal gravitation. All your vectors, like tangential velocity, tangential acceleration, any force is a vector. Velocities, if they show up, are vectors, right? So keep direction on all your vectors and show your units. Although they do often ask for magnitude, so it's kind of nice when you're finding like a velocity or a force or an acceleration and they say the magnitude of it, then you don't have to worry about positive, negative, right? Because magnitude is just absolute value. AP questions are still going to be um, working with like deriving or doing some problem that just has the variables only in it. And when you're deriving, especially on free response questions, there's just going to be certain variables there. Things like at rest and dropped are still useful. Back in Unit 1, we had initial velocity of 0. Now, if something's at rest, we know the forces are balanced, right? If it's dropped, we know that it started off with no velocity, but we would then say something like, oh, well, gravity's acting on it and it falls, so there's no force acting against gravity, so it accelerates, and we could still use that information to good effect. Some things are assumed to be present. The force of gravity is the big one. They want you to be able to find it very easily using mass. Normal force, if it's a situation where gravity would act downwards and normal force would act upwards to balance it, they expect you to be able to do that and find the normal force. Tension sometimes as well, like either balances gravity or there'd be a scenario where something is in equilibrium and the amount of tension would be equal to some other force. Arguments like justifying claims and reasoning, whether it's two individuals or just a statement that you're saying, is it true, is it not true, and why. Substitution equation manipulation is mostly for deriving or anything with equations where you need to solve for something or isolate a variable. And yeah. Okay, just a few things. One that comes up a lot is like if an object's moving, if it has a velocity in a certain direction, that doesn't mean there has to be a force acting on it in that direction at the current moment. At some point, it is true that at some point something acted, some force acted to accelerate the object and give it that velocity that it had in that direction, but it doesn't mean that that force still has to be acting on it. Um, third law pairs can be tricky. The main big one is gravity and normal force. That is not a third law pair because Earth pulls on an object. If the floor also pushes on an object, that would be normal force. Those are three separate objects: the Earth, the object itself that we're talking about, and the floor. So that would not be a third law pair. What would be a third law pair is like the Earth pulls on your shoe and your shoe pulls back on the Earth. That is a third law pair. But if you set your shoe on the table, or well, the floor probably, because it's your shoe. If you set your shoe on the floor and gravity pulls on your shoe, and then the floor also pushes on your shoe with normal force, that is not a third law pair. It's two objects pushing on each other. Static friction is another tricky one. That inequality for static friction equation means it could be less than the maximum value, just depends on what the forces are that might be trying to move the object. So static friction will always try to match or prevent all the forces that are trying to move the object from moving it. Okay. Of course, there might be other things if there's concepts, specific things from throughout the unit that you felt like you struggled with or didn't fully understand. You can ask questions, send me an email. We got lots of resources out there. You can read through the PDF chapters. You can rewatch some of the videos. There's stuff on College Board, AP Classroom. Khan Academy is out there. There's some cool, like Flipping Physics is a cool series on YouTube that's very sort of visual and hands-on. Yeah. And then, of course, your own notes and homework and quiz and lots of stuff to look at. Okay. Let's take a peek at the equation sheet. If you're looking for this, you could print your own out. You're welcome to use the ones in the classroom, but at this point, there's a lot of equations kind of scattered across the equation sheet at various points. It could be nice to have your own printed out. I had some students highlight the questions from various units. I'm fine with that as long as you're not adding or writing anything additional on your equation sheet that you might print print out on paper, you are totally fine to like circle or highlight or look at some things. All right, I'm going to try to get everything. I think we've got everything here. I'm going to go ahead and annotate this so I can do some underlining myself to point out the important equations. All right, so in this unit, center of mass, which I forgot to put on that official content review of all the material we went through. Center of mass equation is on here. There'll probably be like a question on the test that relates to center of mass. Newton's second law is right here as well. It's written a little bit weirdly. Instead of sum of forces equal to mass times acceleration, it's acceleration equals sum of forces divided by mass, but it still works. Reminder that net force is just the sum of forces. When you add them all up and find the total, then that's the net force. It's written in terms of systems, but you could still just use it for a single object, right? You could look at an entire system, the mass of the whole system and the acceleration of the system. You could just as easily do this for one single object. There's universal gravitation, big G m1 m2 over r squared. There's friction. Quick reminder with this one. Friction, you want to split it off into kinetic friction, force of kinetic friction equals mu k times the normal force. So both equations, static and kinetic, both are this, friction and then mu times normal force, but the difference is kinetic friction just equals mu k times normal force. Static friction is less than or equal to mu s times the normal force. So just bear in mind that difference of they give you a generalized equation for friction, and you are expected to know that if it's static friction, you'll use the inequality part of things with the static friction coefficient mu s. If it's kinetic friction is easier because it's just equal to mu k times the normal force. And then spring force is negative k delta x. That one's not too crazy. Just keep in mind your k value is positive. If there's just a negative sign in front of it, so it's like -1 times k. But the k values should be positive. There's centripetal acceleration equal to vt squared over r. They don't do the t subscript there for tangential velocity, which I feel like they should, but it's up to them. So there's centripetal acceleration, tangential velocity squared over radius. Lastly, over here, we do have that third and final circular motion equation. They did get added onto the sheet. So tangential velocity, they still don't put that VT in there. Tangential velocity or linear velocity, right? This is an important distinction between this would be a linear velocity going in a straight line, x or y direction in meters per second. This would be an angular velocity going around and around in a circle, angular meaning around and around the circle in circular motion in radians per second, right? So omega is measuring how many circles per second as it goes around. Velocity is measuring how many meters per second. That's more about the linear or like left, right, up, down type of motion we had looked at in Unit 1. And we'll see more of linear versus angular in Unit 5 when we get to that too. But okay, there's all the equations that you need there. So most of them are kind of concentrated right here, but there's kind of the one odd one over there. All right, let's get rid of this. Now, we're going to do just a few reminders on tips and things to do for dynamics problems. All right, so I'm not going to maybe hit on everything here. Like some stuff like center of mass is fairly straightforward when you do it, and you can go back and look at the problems. There's nothing particular I wanted to say about most of those things. But yeah, let's start with just a reminder on we could do angled forces. Let's let's actually start a little further back. Let's with summing forces. So for the sum of forces equal to mass times acceleration, we would do separate x and y equations. So your sum of forces in the x direction should not include should not include vertical forces. Your sum of forces in the y direction vertically should not include horizontal forces. Do those separately. Or clockwise, counterclockwise. That direction would be Atwood's machines. Once we get to that, we'll remind you of that. Or in out. That would be circular motion. Sometimes we say any forces inwards are positive, any forces outwards are negative when we're looking at centripetal force for circular motion. Okay, so that's a reminder just on general Newton's second law, summing forces. Just a quick one on third law pairs. That is specifically two, no more, two objects putting forces on each other. All right. Let's talk a little bit about, well, we'll throw, I guess we talked about friction already. Yeah, I kind of mentioned, and you can go back to your notes. Like all of this is in your notes. I just am trying to like remind you of some things, but the friction stuff we kind of had talked about. And all right, so systems do a sum of forces either for the individual objects in which case you include internal forces, but you would only include forces or any forces acting on that particular object. You still want to look at, if I just pick one object in my system, just one of them to look at with the forces, the sum of forces, I only want to include forces that are acting directly onto that object, right? Or you could do sum of forces. If you end up not wanting to do the individual objects, you could do sum of forces for the whole system. Which would then be only external forces, not the internal. This is really handy for something like tension in an Atwood's machine. If you have tension in the string connecting the objects in an Atwood's machine, summing forces for the whole system is often a good idea if you don't want to deal with that force of tension, if you don't really want to do anything with it, if you'd like to avoid having it show up in your equations. Okay. Let's go specifically to Atwood's machines. Just going to do a few reminders here. One is clockwise or counterclockwise directions. So we don't really care for Atwood's machines if a force is acting up, down, left, or right. For the purpose of all those connected objects in the Atwood's machine, we use clockwise, counterclockwise directions. So if a force is trying to get the whole thing to go clockwise around the pulley, that's a clockwise force. If the force is trying to get the whole thing to go counterclockwise around the pulley, that is a counterclockwise force. Also, just a quick reminder, the force of tension, and this works for any tension you find, but especially for Atwood's machines too. Force of tension in a particular length or section of string. So if you have one particular string connecting two objects, the force of tension in that section of string or rope or whatever is the same all throughout. That tension does pull it pulls on both ends, right? So the tension might pull one way, like the tension on one end of the string pulls to the left on one block, and then over on the other end, that same tension pulls to the right on the other block. But the amount of tension is the same throughout. What else here? Oh, friction. Friction on the pulley acts on the whole system, not individual objects. And you're not always going to have friction, but if it did show up from the friction on the pulley, it would act on the whole system. Versus like something like friction on the table, friction from a table could act on the individual objects by themselves. All right. I think that's mostly it for Atwoods. Let's do a couple reminders on ramps. Trying to round up as much as I can here for these tips or reminders. For ramps, make sure we treat the surface of the ramp as the x direction. Anything going up or down the ramp, we should consider that as like positive or negative x direction, which means normal force perpendicular to the ramp is then y direction. What that means is we have to split gravity, weirdly, into components, right? So of all the forces to split up, we're so used to gravity just being downwards in like the y direction that when we change our x and y directions by having the surface of the ramp be the x direction, we have to split the force of gravity into components. And I'll remind you once again, even though it's in the notes and in the other videos, force of gravity, FGX, along the surface of the ramp, acting down the ramp, uses the cosine of the angle. Oops, see, I'm already mixing them up. I'm so used to cosine for x. Uses the sine of the angle theta at the bottom of the ramp times mg, the total force of gravity. And FGY, the part of gravity pulling the object directly into the surface of the ramp, uses the cosine of the angle theta at the bottom of the ramp times mg, the total force of gravity. So just keep those in mind because they're swapped from we often have cosine for x, sine for y, but they are different here. And I would not try to go through the reason why in every single ramp problem. If you try to go and make a bunch of triangles and similar triangles and find exactly what the angle is with your gravity components in your gravity triangle, it's going to be a pain. So I would just say no or memorize that for the x component along or down the ramp, sine theta mg. For the part of gravity pulling into the surface of the ramp, cosine theta mg. Okay, what else here? I guess we'll just say, remember that normal force is pretty much always just going to be equal to FGY, not equal to the whole force of gravity. The entire force of gravity is not balanced by normal force. Just the part of gravity pulling into the surface of the ramp is balanced by normal force. And then lastly, circular motion things. A few main reminders with that is that there must be an inward force. And once you sum up all those forces, you get that force FC, which is, of course, the sum of all forces acting in the in or out direction. According to our equations, just a general thing to remember is if tangential velocity increases, the centripetal force must also increase. Something like our circular motion equation, centripetal force equal to mass times centripetal acceleration, but I'm going to write acceleration as vt squared over r, you're generally not going to see the mass of the object suddenly changing. You're generally not going to see the radius of the circle suddenly changing. So if those remain the same, then when vt gets bigger, centripetal force must increase. That's why you spin something on a string faster and faster. There's got to be more and more and more tension as it spins. What else here? For circular motion, I guess we'll throw in orbit reminders. So, well, we'll do a few things. We'll say for orbits, just kind of the very end of what we did, but we'll pop it in here with circular motion. For orbits, the centripetal force is just equal to the force of gravity, specifically using the equation big G m1 m2 over r squared. And that centripetal force, you can simplify if you set this force equal to mass times vt squared over r. You can cancel some things out. So if m2 was, well, I guess you have to get a little specific of if m1 is like the planet and m2 is the moon, this is the thing in the middle, and this is the orbiting object. Mass 2 would show up on the other side of the equation, and you can simplify. You can go back to the notes too if you're wondering how I magically appeared with this equation. You can go check the orbit notes or gravitation and orbits notes. Okay. So it can simplify down to that. You can get the universal gravitation equal to mass times centripetal acceleration, and it boils down to, well, a simplified version of it for orbits can be seen on that far right. You don't want to use that for just any circular motion, right? It would only be for a circular orbit with gravity. Okay. Yeah, there's a lot of things that could be said here, of like, know your equations, know how to work with them. Circular motion often combines multiple equations together because you've got centripetal force equals mass times acceleration. You've got centripetal acceleration equals vt squared over r. You got three separate circular motion equations to work with. Okay. I think that's most of the stuff I wanted to address with that. I guess I'll throw a reminder in here for like vertical circles. They're not a ton of problems, but vertical circles include the force of gravity in the sum of forces in or out, specifically when you're at the top or at the bottom of that circle. Just a quick, right? If you're looking from the side and something goes around and around and around like this in a vertical circle, right here and right here, you've got gravity acting inwards at the top or gravity acting outwards at the bottom. Okay, cool. I think that's most of the main reminders I wanted to give. I just wanted to kind of run through some of the problems you'll see, right? You'll see like probably 2 or 3 circular motion problems. You'll see at least one ramp problem. There'll be an Atwood's machine somewhere in there, and systems of objects in general, right? Any system you find, multiple objects. You could do the sum of forces for individual objects or for the whole thing. There will be a third law problem on there. Summing forces is definitely important. And also, right, equilibrium. I'm not going to write it on here, but just reviewing or knowing equilibrium where, hey, if the forces are balanced, if they add up to 0, there's no acceleration. We have like horizontal equilibrium, vertical equilibrium. If our object is at rest or in constant velocity motion, being aware of that and using that to be able to solve for things. Say, hey, I know I'm in equilibrium. The forces are balanced, so gravity equals normal force or something along those lines. Okay. Cool. Well, I'm going to call it there. I don't want to make this a super duper long video, but just wanted to review some things, go over the topics we've covered in Unit 2, some of the equations from the sheet, and some reminders for your problem solving. All right. Well, if you're watching this in class, I will see you back in class, and we'll try to get ready for and prep for the test, the unit test. Don't forget to, if you have questions on any of this or just anything at all, you can always reach out to me. Or there's also that Padlet on Schoology below the agenda. You can submit questions anonymously on there. Yeah, I think that's it. Well, thanks for watching, and we'll see you for the unit test, and then when we move on to Unit 3.